Hello, good day. For today, we'll be continuing the discussion about series, and this time we're going to discuss integral tests and estimates of the sums. So let's have the integral test and estimate of the sums. So in general, it is difficult to find the exact sum of a series. We were able to accomplish this for geometric series and for some telescoping series because in each of those cases we could find a simple formula for the nth partial sum S sub n. But usually it isn't easy to discover such a formula. So take note that for geometric series, the formula is for geometric series, the sum S sub n is equal to a sub 1 over 1 minus r. Now take note that the condition is that your r should be in between negative 1 and positive 1. For telescoping series, your sum is the limit of your some terms of the series wherein your b to the infinity would be approaching 0. So you're just going to take some few terms of the telescoping series that was not eliminated or cancelled out by the expression. So now let us consider the integral test. So we begin by investigating the series whose terms are the reciprocals of squares of a positive integer. So that is the reciprocal 1 over the squares of positive integers, so n squared. So 1 over n squared. So we start with 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared and so on. So there's no general formula for the sum S sub n of the first n terms, but the computer-generated table of approximating values given in the margin suggests that the partial sums are approaching a number near 1.64 as n approach infinity. And so it looks as if the series is convergent. So all of the sums are being considered here. So 1.4636 if we use 5 terms, 1.5498 if we use 10 terms, and so on. So as n approach infinity, it approaches 1.6447. So this is the sum of all of the terms in the series. We can confirm this impression with a geometric argument. So figure 1 shows the curve y equal to 1 over x squared and the rectangles that lie below the curve. So 1 over 1 squared, 1 over 2 squared, 1 over 3 squared. So if we are referring to the width 1, because your n is 1, so the area would be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared and so on. The base of each rectangle is an interval of length 1 and the height is equal to the value of the function 1 over x squared at the right endpoint of the interval. So, the sum of the areas of the rectangle is 1 over 1 squared plus 1 over 2 squared and so on and so forth. If we exclude the first rectangle, so we start with this one, we exclude the first rectangle. So we start with 1/4 followed by plus 1 over 9 squared. 1 over 9, sorry. So this improper integral is convergent and has a value 1. So the picture shows that all the partial sums are less than 1 over 1 squared plus the integral of 1 over x squared from 1 to infinity dx. Thus, the partial sums are bounded. We also know the partial sums are increasing because all of the terms are positive, and therefore the positive sums converge. So since it is a monotonic sequence, so the series is convergent. The sum of the series limit as partial sum is also less than 2. So the summation of 1 over n squared equal to 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared is less than 2. So now, let's look at the series. Another series, 1 over square root of n. So this would be 1 over square root of 1 plus 1 over square root of 2 plus 1 over square root of 3 and so on. If we're going to use same software to generate the partial sums, you can see that as you increase your n, the sum also increases. So the table of values of S sub n suggests that the partial sums aren't approaching a finite number. So we suspect that the given series may be divergent. So again, we use the picture for the confirmation. Figure 2 shows that the curve y is equal to 1 over square root of x, but this time we use rectangles which lie above the curve. So this would be greater than, because it is higher, it is bigger than the actual curve. So the base of each rectangle is an interval of length 1, and the height is equal to the value of the function 1 over square root of x at the left endpoint of the interval. So the sum of the areas of all rectangles is 1 over square root of 1 plus 1 over square root of 2 plus 1 over square root of 3 and so on. So this completes the integral 1 over square root of n, or the summation of 1 over square root of n. This total area is greater than the area under the curve y is equal to 1 over square root of x for x greater than or equal to 1, which is equal to the integral of 1 over square root of x dx. But we know that this improper integral is divergent. So it is a p-series, no? So in other words, the area under the curve is infinite. So the sum of the series must be infinite, that is, the series is divergent. So to properly quote the integral test, so the same sort of geometric reasoning that we used for these two series can be used to prove the following test. So for the integral test, suppose f is a continuous positive decreasing function on the interval from 1 to infinity, and let a sub n is equal to f of n. Then the series summation of a sub n for n equal to 1 to infinity is convergent if and only if the improper integral of f of x dx from 1 to infinity is convergent. In other words, if the integral of f of x dx from 1 to infinity is convergent, then the series summation of a sub n for n is equal to 1 to infinity is convergent. Similarly, if the integral from 1 to infinity of f of x dx is divergent, then the summation of a sub n is divergent. So let's have this for example. So let us test the series summation of 1 over n squared plus 1 for n is equal to 1 to infinity for convergence or divergence. So the function f of x equal to 1 over x squared plus 1 is continuous, positive, and decreasing on 1 to infinity. So we use the integral test. The integral of 1 over x squared plus 1 dx from 1 to infinity is the integral of 1 over x squared plus 1 dx from 1 to t as t approach infinity. So this becomes the limit of the integral of du over u square plus 1 is arctangent u. So we have the arctangent of x from 1 to t where t approach infinity. So arctangent of infinity is approaching 90 degrees or pi over 2 minus arctangent of 1 is pi over 4. So pi over 2 minus pi over 4 is just pi over 4. So this is real. So thus, the integral of 1 over x squared dx from 1 to infinity is convergent integral. So by integral test, the summation of 1 over n squared plus 1 is convergent. So the series 1 over n raised to p is called the p-series. The p-series summation of 1 over n raised to p is convergent for p greater than 1, and it is divergent when p is less than or equal to 1. So let us now consider summation of 1 over n cubed for n equal to 1 to infinity. So this would mean we have 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed and so on. This is convergent because it is a p-series with p equal to 3 greater than 1. While the series 1 over n raised to 1/3, so we have p is less than 1. So summation of 1 over cube root of n equal to 1 plus 1 over 2 raised to 1/3 plus 1 over 3 raised to 1/3 plus 1 over 4 raised to 1/3. This is divergent because it is a p-series with p equal to 1/3, which is less than 1. Let us now consider the series ln n over n if it converges or it diverges. So the solution is we consider the function ln x over x. So this is positive and continuous for x greater than 1. And this is, but it is not obvious whether f is decreasing. So to determine whether it is decreasing over the interval n greater than 1, so we differentiate this. So differentiating f of x, so that would be ln n over n, so that would be 1 over x squared times v du minus u dv. So the derivative of ln x is 1 over x times x, and then minus ln x times 1. So we have 1 minus ln x over x squared. So this is, so 1 minus ln x. When x is 1, it would be 1 over 1 squared. So when x equal to 1, so this would be 0. When x is 2, it would be 1 minus ln 2 over 2 squared. So, and then when x is 3, 1 minus ln 3 over 3 squared. So this expression would be negative, meaning it is decreasing when x is greater than 2.718, when it is greater than e. So thus, f prime of x is less than 0 when ln x is greater than 1. So it would be greater than 1 when x is greater than e. So it follows that f is decreasing when x is greater than e. So we can just disregard the first term, x is equal to 1 and x is equal to 2, because beyond that, it would be decreasing. So we have ln x over x dx from 1 to infinity. So it would be, so we set your u to be ln x, and your du is 1 over x dx. So we have u squared over 2, or ln x squared over 2. So we evaluate ln x squared over 2. So that's ln t squared over 2 as t approach infinity, minus ln 1. ln 1 is 0, so this is minus 0. And as t approach infinity, so this would be infinity. So this is not real, so that would be divergent. So since the improper integral is divergent, the series ln n over n is also divergent by applying the integral test. Estimating the sum of the series. So suppose that we have been able to use the integral test to show that the series summation of a sub n is convergent. And now we want to find an approximation to the sum of the series. Of course, any partial sum S sub n is an approximation to S because the limit of S sub n as n approach infinity is the sum. So, but how good is such approximation? To find out, we need to estimate the size of the remainder. So, the difference R sub n is equal to S minus S sub n, which is the difference. So the terms that we have not considered are a sub n plus 1, a sub n plus 2, a sub n plus 3, and so on. So the remainder R sub n is the error made when S sub n, the sum of the first n terms, is used as an approximation to the total sum. So that would be the terms that we have disregarded. So we use the same notation and idea as the integral test, assuming that f is decreasing on the interval from n to infinity. Comparing these areas of the rectangles with the area under y equal to f of x. For x greater than or equal to n, we see that r sub n would be a sub n plus 1, a sub n plus 2 plus, and so on and so forth, which is less than the integral of f of x dx from n to infinity. Similarly, we see from the figure that r sub n is equal to a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3 and so on, which is greater than or equal to the integral of f of x dx from n plus 1 to infinity. So we have proved the following error estimate. So to remainder estimate for the integral test, suppose that f of k is equal to a sub k, where f is the continuous positive decreasing function for x greater than or equal to n, and the summation of a sub n is convergent. If r sub n is equal to s minus s sub n, then your r sub n would be in between the integral of f of x dx from n to infinity, and this should be higher than the integral of f of x dx from n plus 1 to infinity. So, very small. So, approximate the sum of the series summation of 1 over n cubed by using the sum of the first 10 terms and estimate the error involved in this approximation. So, r sub n is the error equal to the which is in between 1 over the sum from n plus 1 to n. And how many terms are required to ensure that the sum is accurate to within 0.0005. So in both parts A and B, we need to take the integral of f of x dx with f of x equal to 1 over x cubed, which satisfies the conditions for the integral test. So we integrate x raised to negative 3 dx. So the integral would be x raised to negative 2 over negative 2 or negative 1 over 2x squared. We will be evaluating this from n to t as t approach infinity. So we're going to consider the right side terms that has not been included. So limit would be the limit from negative 1 over 2 raised to n plus 1 over 2n squared as n approach n. So as t approach infinity, that would be 0. So the resulting term would be 1 over 2n squared. Approximating the sum of the series by the 10th partial sum. So we're going to use up to for n is equal to 10. So if we are going to manually add 1 over n cubed from 1 to 10, it would be 1.1975. So you can use your calculator for this. Summation of 1 over x cubed, where x is from 1 up to 10 with the step equal to 1. According to the remainder estimate, your r sub 10, the remainder would be less than or equal to the integral from n to infinity. So that would be 1 over 2n squared. So 1 over 2 times 10 squared, or 1 over 200. So the size of the error would be 1 over 200, or 0.005. If we want the error to be up to 0.0005, so from the formula that we have for the error 1 over 2n squared, we want it less than 0.0005. So we can use cross multiplication because all of this would be positive. So we have 2n squared is equal to 1 over 0.0005. So your n squared would be 1 over 0.001, or 1,000. So your n would be the cube root of 1,000. So approximately 32 terms will ensure that the accuracy would be 0.0005. We round it up so that we would have a better accuracy. So 31 terms would not be sufficient for the accuracy. So to reach at least 0.0005, we use 32 terms in the series approximation. So if we add s sub n to each side of the inequality, we get s sub n is equal to s sub n plus the integral of f of x dx from n plus 1 to infinity is less than or equal to s and less than or equal to s sub n plus the integral of f of x dx from n to infinity. Because s sub n plus r sub n is equal to s, the inequalities in 3 gives the lower bound and an upper bound for s. So they provide a more accurate approximation to the sum of the series than the partial sum s sub n does. So that's all for the integral test.